You're welcome to Enoch's videos, and today I'm presenting about molecular polarity. There are key words here that we need to understand: a molecule and polarity. I'm assuming that you all know what molecules are, but let me briefly talk about polarity. What do we mean by polarity? Polarity results from unequal or uneven partial charge distribution between various atoms in a compound. That's how it comes about. So we all know that molecules contain polar bonds, but it's not a must that all molecules are polar. There are some molecules that have polar bonds, but they are themselves non-polar, as we shall see. So what are we saying here? So that whether a molecule itself is polar or not, there's an easy method that we can use to establish whether it is polar or non-polar. How? How do we do it? We say that if there are non-polar bonds, a molecule is totally non-polar. There's no need to actually even to reason there. Then, if there are polar bonds and the molecule is symmetrical, that is, if you look at the molecular geometry and it hasn't been affected either by lone pairs through changing the bond angles, then we say it is symmetrical, as you're going to see. In that case, the molecule will be non-polar. However, if there are polar bonds and the molecule is asymmetrical, asymmetrical, the molecule is polar. Yeah, let's look at it and see. So we're going to use a link which I'm going to open right now and try to build up some structures and see what I mean by having unequal or uneven partial charge distribution, and then we also identify which molecules are polar and which molecules are non-polar. I will build some simple molecules. Let's start from the simplest. Let's start with hydrogen gas, and we look at how the electron density or the charge is distributed. I'll build hydrogen gas. So this is hydrogen, this is hydrogen. Let me put a bond in between. So that is a bond in between. And let's try to find out the charge distribution, electron density. Or when you look at hydrogen, the electron density is uniformly distributed. First of all, these are hydrogens. They have the same electronegativity, so there's no atom that attracts the electron density or electron cloud more towards itself than the other. So because there's no overall net charge distribution or overall electron density on one atom, therefore this molecule, we say that it is non-polar. Let me give you another example. Let's look at chlorine gas. Let's look at chlorine gas. Let's look at chlorine gas. Let's build chlorine. So that is a chlorine atom. This is a chlorine atom. Let's try to form bonds in between. Sorry. Let's try to form bonds. So that is chlorine gas. And let's try to check out the distribution of the electron density around its atoms. Just look that the distribution is even. The distribution of electron density is even around chlorine. So there's no net charge distribution. Therefore, we say that this molecule is non-polar. Although the bonds are polar, or the bond is polar, but the whole molecule is non-polar. Let's look at another. Let's try hydrogen chloride. Let's try hydrogen chloride. So this is chlorine, and let me add hydrogen. Let me add hydrogen. So this is a hydrogen that has been added, and let's try to check the electron density or distribution around this molecule. Just look at it. In this case, the electron density is more towards the chlorine atom than the hydrogen. That means the distribution is uneven. There is uneven distribution of the electron density in this molecule. Therefore, this molecule shall say that it is polar. Now that there's a net charge distribution when you look at this. Let's look at other molecules that have more than two atoms. Let's look at some molecules that have more than two atoms. We shall use boron fluoride. Let's use boron fluoride and we see whether it is polar or non-polar. I'll choose boron. Then let's add also the fluorine. Let's add the fluorine. So there are three atoms. Let me try to put that bond. Okay. Let's check the electron density. Just a moment. Then first add the fluorine again. Add the fluorine again, sorry. Then add the fluorine. Okay, so we have that. So let's say there are three of them. Have that. Let's first of all get the idealized structure. So this would be the structure of boron fluoride. Let's try to rotate it and you see, which is a trigonal planar molecule. Now let's try to check its symmetry. Let's look at its symmetry. In this case, when you look at the symmetry, it has symmetry. In others, it can be divided into equal portions. Hopefully you can see the first portion here, the second portion, and the third portion. So it is symmetrically arranged. So what does this mean? It means that there is no overall net charge distribution on this molecule. Let's try to add on the electron density. Look carefully. So you can't say that the electron density has been so much distributed on the side of this fluorine, nor this fluorine, nor this fluorine. So there's no net charge distribution. And this molecule, we say that is symmetrically arranged. Okay, it's symmetrically arranged, and therefore there's no overall net charge distribution. And we can comfortably say that this molecule, it is non-polar. Although the bonds may be polar, but the whole molecule, we are saying that it is non-polar. Okay, let me just briefly show you boron and fluorine. When it is one boron atom and fluorine atom, and then we see whether there is an overall net charge distribution or it's not there. Okay, let's just do that. Let me remain with one. Let me add bonds. Okay, let me just build it again. So we have fluorine there, and let's add boron too. Let's add boron. This is boron. Let's form a bond there. So let's try to establish the electron density and see whether it will be uniform. So let's get the electron density. Wow, look carefully. And just to view. Look carefully. When you look at what we have, is that we don't have an even distribution of the electron density. We don't have an even distribution of the electron density. So what does this mean? It means that the bond the bond between fluorine and boron, the bond between fluorine and boron is polar because of the uneven distribution of the bonding electrons. However, if it is boron fluoride with the 3 fluorine atoms, the molecule is non-polar. Let me add more fluorine. Let me add more fluorine so that you can see it. Fluorine. This is fluorine. This is fluorine. Let me add the bonds. Let me add the bonds. Let's get the idealized structure. So that is the structure. Sorry, that is the structure. And then when you look at the electron density, in others, there is in other words, the distribution of electron density is uniform throughout the whole structure, and then in that case we say that there is no net charge or no overall net charge distribution, and this molecule will be non-polar, although the bonds are polar. I guess you're getting my point. I'll give you another example. Let me give you an example of water. Let me give you water. In water, we have oxygen and we have hydrogen. So that is our oxygen atom. And let's add the hydrogen. Let's add the hydrogen. That is hydrogen, another hydrogen. Let me put them there. We have a bond there. Sorry. We have a bond here. And then also have a bond there. Let's first of all get the idealized structure. That is the idealized structure of water. That's how we all know that it has a bent structure, although it has a 4-electron domain. Hopefully we all know that. Now, let's try to check on the electron density around this molecule. Electron density. Look, it is more on the side of water. In other words, the electrons are more distributed on the side of water rather than hydrogen. So this molecule, the overall, shall say that it is a polar molecule because there's an overall net charge distribution. The electrons are more on the oxygen than it is on the hydrogen. So the molecule is polar. The molecule is polar. Remember, water has lone pairs, and those lone pairs affect the distribution of the bonds, and therefore, so in summary, some molecules can be having polar bonds by themselves being non-polar, and we can have those that have polar bonds but still being polar. So that one is very, very possible. Let me give you another example. Don't get tired. Let me give you another example. Let's build tetrachloro methane, that is carbon. Let's add chlorine, 4 of them, but we shall begin with 1 chlorine atom. So chlorine and carbon, that is a polar bond. Let's check the distribution of the electron density. You find that chlorine attracts more of these bonding electrons towards itself than carbon. So this bond is polar, right? It is polar. Let's add more chlorine atoms. That is 1, 2, 3. That, and that. Sorry. That. Let's get the idealized structure first of all. So that is the idealized structure, which is a tetrahedral structure. However, let's look at how the electron density is distributed. Electron density is distributed, and see whether the molecule itself is symmetrical. Just look. The distribution of the electron density is uniform. So this molecule, we can say that it is non-polar, although the bonds are polar. Hopefully you are getting me. Let's check the symmetry clearly. It is symmetrical, but the bonds are polar. The molecule is symmetrical, and therefore the whole of this molecule here is non-polar. I guess you get what I'm saying. So that is concerning the distribution of the electron density. So we need to accept that the molecules that are non-polar but having polar bonds, and there are molecules that are polar but still also having polar bonds. All right, I'll take you back. I'll take you back. So that is another aspect that we need also to know. Then, when you come to the periodic table, we need to know that fluorine is the most electronegative element with a measure on the inner scale that is 4.0. So downwards, or as you move down, the electronegativity definitely decreases. As you move downwards, electronegativity decreases. So if you're given some molecules and you have your periodic table, you can easily tell that the one at the top is more electronegative, and those that are down are less, or their electronegativity keeps on decreasing. That is an aspect that you need to have studied, or that you must have in your mind. That as you move up, electronegativity goes high. As you move down, it goes low. But again, that is as you move from one period to another period, just downwards. But as you move across the periodic table, that is from left to right, you find that electronegativity increases. That is an aspect that you need to master. So what am I saying? I want to talk about briefly the bond and the molecule. The bond, once you find that in the molecule, the bonds are non-polar, definitely the molecule itself is non-polar. If you find that the molecule is polar, further find out whether the molecule has symmetry. If it has symmetry, then it is non-polar. Then still find out if the molecule has polar bonds and the molecule is asymmetrical, then it implies that the molecule is polar. Right. I guess you have picked it. In case you haven't got what I'm saying, still you can contact me on my WhatsApp. You can even call. You can also visit my website. However, I encourage you to share this video with a friend. Share, share, share. Thank you very much for watching Ernst's videos. Don't forget to subscribe. Bye bye. Bye bye.